Hi, my name's Brian Northern. I'm a contract image processing developer. I have my own small company called True North Intelligent Algorithms, and I'm going to do a presentation today called Flexible Deconvolution Using Open Source in 2022. And this is pre-recorded April 27th, 2022, so a few of the links and things may change, hopefully for the better, before um, the actual day that this is shown. Most important thing is that if you have any questions about this presentation or really anything else about imaging, go to the image.sc forum. Any questions about this deconvolution presentation, please flag me. Maybe I'll even start a thread myself about it, just to make it easier for people to find this presentation. This presentation is going to be on GitHub, and the useful thing about getting this, taking a look at this presentation on your own time is all these links are live, so you can see like my GitHub and the ImageJ forum and stuff. So hopefully that's useful for you to be able to find things. So the inspiration for this was I did a presentation 7 years ago now in 2015 called Flexible Deconvolution Using ImageJ Ops, and I wanted to, a lot has happened in the open source community and with open source deconvolution since then, so I thought it was time for an update, and this is a good opportunity. So it became, instead of just with ImageJ Ops, it's now with open source. Quick outline. We're going to talk about what is deconvolution, talk about some of the problems you face when doing deconvolution, finding the PSF, dealing with noise, edges, stopping criteria, and then talk a little bit about state of open source deconvolution right now, and then some current and future goals. And I'll go over some results. And I should also really emphasize that you know, the open source world is exploding, and there's probably all kinds of things I don't know about, and I'm really like a user of deconvolution. As well as a developer, so all the stuff I missed, please flag me and tell me about it. You know, it might be better than the stuff I'm talking about today. So quickly, what is deconvolution? It's a procedure used to reverse convolution, and convolution is basically blurring, the blurring we see with the microscope. Deconvolution is doing the opposite, getting rid of the blurring, and we like to say it improves measurements. Do we have evidence of that? I'll talk a bit about that at the end. And deconvolution belongs to a broader class of problems called restoration. These are really difficult problems because you also have to consider noise. So restoring the true signal in the presence of both blur and noise is really hard. Because two things, we say the problem is ill-posed, and that means it cannot be solved perfectly. Microscopes are band limited, so some frequencies aren't passed through. And then there's also different types of noise which get added, end up in the image, and that cannot be solved by reverse convolution alone. So here's a picture of a point spread function. This is actually like the hardest part of deconvolution. Well, I mean, not the hardest part, but the part I see where people always go wrong. It's really hard to measure your PSF, because a lot of times people measure noisy PSFs, and if you're measuring a PSF, you need to do a little bit of cleaning up of it, and you need to do that properly, or else you're going to get some severe artifacts. If you're doing a theoretical PSF, you just got to make sure all the parameters are right. Very, very often I see metadata issues. So it's important to have a way to either measure or generate a PSF. I've listed some software here that may be useful. Only a 10-minute presentation, so I don't really have time to talk about them in detail, but the links are here. So if you want to have any questions about PSF generators, let me know. And then there's also approaches that we use to generate a PSF from beads. So there's actually there's been some good questions over the years on the ImageJ forum on that. It might be under the topic distilling. So any questions about getting a PSF from beads or theoretical PSFs, ask on the forum. Here's a quick slide of the imaging process. We have a known true object, and when it goes through the microscope, it gets blurred. But then there's not just blur, there's also noise. So convolution with the OTF of the PSF of the microscope attenuates a lot of the high frequencies, and deconvolution attempts to restore them, but because the microscope is band limited, we lose some information. And since the noise didn't come from mathematical convolution, trying to undo that process can actually amplify the noise. So here's another example where we image and then there's noise too, so it's a real mess. And again, simple way of solving this problem would be just to solve the, you can solve the equation in the frequency domain, but that causes this noise amplification that I've mentioned a couple of times. So a really common approach is to use an iterative approach where we use optimization to solve the problem in steps. And one of the most common approaches is called Richardson Lucy. If you've looked into deconvolution, you've probably heard that term. It's also known as a maximum likelihood estimation, or a particular solution for maximum likelihood estimation. And here's a quick look at Richardson Lucy iterations. Several implementations of Richardson Lucy available. Again, here are some links to some of them. A new one that just came up is Red Lionfish, which is OpenCL and compatible with Dapari. I've been working on an ImageJ Ops version for many years, and also lately a Klege version, which is again OpenCL GPU. So here's some links to some open source Richardson Lucy, and quickly the results of a regularized. Oh no, this is just a Richardson Lucy on a noisy beat image, and you can see you get some noise things. And you know, noise has been a topic of conversation. If you follow Twitter, you'll notice that sort of the microscopists on side Twitter, there's been some conversation about how to figure out where to stop the Richardson Lucy process in the presence of severe noise. Again, if you have questions about that, ask on the forum. And if we use the Richardson Lucy with total variation, is a version of Richardson Lucy that's modified to better handle the noise. And some links to some versions of that. And this diagram here shows Richardson Lucy with total variation. Another thing I need to mention is edge handling. Boundary conditions are actually really important, especially if your object, you don't image your entire object. You can get severe artifacts if you don't consider edge handling. So if you have sort of these like really blocky, sharp square artifacts in your image, it might be a edge artifact issue, and you could solve that with non-circulant deconvolution. And then how do we make it fast? There's a couple of algorithmic acceleration schemes we could use. Also lately, big topic, hardware acceleration. Everybody's implementing everything in the GPU. So there's probably like 50 new Richardson Lucy GPU implementations like released every month. So in 2.15, we had a bunch of goals that we wanted to do. And I think one way or the other, we like accomplished a lot of them. We wanted to get on the GPU. We wanted to have diffraction-based PSFs, and we have some of those in Ops. We have some GPU in Klege. And we want to do benchmarking. The big lab, BIG lab, here's a link to some really good benchmarking images. I wasn't involved in this, but I certainly take advantage of those images. So that's a good source. And then here's some results. I showed these 7 years ago on the McNamara sets. PSF was created using PSF generator. Just some deconvolution results. And I'm rushing through this now because I've got like 1 minute left. Here's some of the results. These are actually the results we generated 7 years ago. And some new stuff. I'm going to quickly show Dapari here. So here's this is a new little simulation I just did, and I'm going to be talking more about this tomorrow. This is like a resolution test in Dapari, and here is sort of a 3D view of a deconvolved image in Dapari. This is a simulation. This is the original image, and this is after deconvolution, and we also have the ground truth here. So this is kind of cool. Okay, I think I ran out of time. Thank you for listening. We're doing a Dapari thing tomorrow if you want some more detail about these simulations.